Bernoulli's theorem is an energy statement for an ideal flowing fluid. It says that along a streamline, the pressure term, the kinetic energy term, 1/2 rho versus squared, and the gravitational term, rho gz, add up to a constant. The assumptions are steady flow, incompressible fluid, negligible viscosity, and analysis along a streamline. We will prove this using work and energy. Then apply it to two important cases. The first case is pressure variation with height in a static liquid column. The second case is a hydraulic brake, where pressure is treated as constant and a larger area gives a larger force because height effects are negligible. Consider a fluid element moving along a streamline from section 1 to section 2. At section 1, the pressure is P1, area is A1, speed is V1, and height is Z1. At section 2, the corresponding quantities are P2, A2, V2, and Z2. We will examine a small time interval dt. Because the fluid is incompressible, the volume entering section 1 in time dt equals the volume leaving section 2 in the same time. This common volume is dV, equal to A1 versus 1 dt, and also equal to A2 versus 2 dt. Now count the work done on the fluid element. The pressure at section 1 pushes the element forward, doing positive work P1 decivolt. The pressure at section 2 opposes the motion, doing negative work P2 decivolts. Gravity does work equal to minus the weight of the element times its rise in height. So the gravitational work is minus rho g dV times Z2 minus Z1. The work energy theorem says total work equals the change in kinetic energy. The kinetic energy change is 1/2 rho dV times versus 2 squared minus versus 1 squared. Equating the pressure work, gravity work, and kinetic energy change gives the energy balance for the fluid element. Cancel the common volume dV and rearrange the terms. All quantities at section 1 appear on the left, and all quantities at section 2 appear on the right. This gives Bernoulli's equation. This is the proof. Now apply Bernoulli's equation to the first case, a static liquid column or an open tank. If the fluid is at rest, the velocity is zero everywhere. Bernoulli's equation reduces to P plus rho gz equals a constant. Taking a small height change gives dP dz equals minus rho g. This means that with upward vertical coordinate z, pressure decreases as you go upward. This is where the height convention matters. If we measure h downward as depth below the free surface, then pressure increases with h. At a depth h below the surface, the pressure is atmospheric pressure plus rho gh. This is the familiar result that a taller or deeper water column produces greater pressure. This is also the reason a tank drains with speed determined by height. Apply Bernoulli from the free surface to a small outlet hole, both open to atmospheric pressure. The pressure terms cancel, and the lost gravitational head becomes kinetic energy, giving Torricelli's law, V equals square root of 2 grams h. Here the height term is the dominant driving term. This connects to the tank comparison. A tank that maintains a larger height maintains a larger exit velocity. That is why the tank preserving its water height can empty first even if another tank's level appears to fall faster. Now consider the second case. A hydraulic brake. A small master piston of area A1 is pushed with force F1. This creates pressure P equal to F1 divided by A1. In an enclosed liquid, this pressure is transmitted throughout the fluid. This is Pascal's law. At the wheel piston, the same pressure acts on area A2. So the output force is F2 equals P times A2, or F1 times A2 over A1. Therefore a larger area gives a larger force. This force multiplication does not violate energy conservation. The small piston must move a longer distance, while the large piston moves a shorter distance. The displaced fluid volumes are equal. A1S1 equals A2S2. Ideally, the work input equals the work output. F1S1 equals F2S2. What about the pressure due to height? It is still present in principle. But in a brake system the vertical height difference is small, and the pressure created by the pistons is large. The term ρg delta H is therefore very small compared with the applied hydraulic pressure. So it is neglected. As a result, we treat the pressure as the same at all points in the brake line. Let us compare the two cases. In the tank or static column, pressure differences come mainly from gravity and height. We keep the ρgz term. Pressure increases with depth, and this pressure head can create outlet velocity. The area of the tank does not change the pressure at a given depth, but it changes how fast the height falls and therefore how the drainage time evolves. In the hydraulic brake, pressure comes mainly from an external piston force, not from elevation. The height term is negligible, so pressure is treated as constant. The same pressure acting on a larger area produces a larger force. This is force multiplication, while energy is conserved through displacement trade-off. Both scenarios come from the same fluid mechanics principles. In the tank, the gravitational term dominates. In the brake, the externally created pressure dominates and the gravitational term is ignored. The key lesson is: start from Bernoulli or hydrostatics. Identify the dominant terms, and neglect only the terms that are genuinely small.